For our second talk this morning, and this talk is Martin Steinheimer, who's going to talk about stochastic representations of model uncertainties.
Yeah, hello everyone. As it is in the title, I will talk about the stochastic parametrizations we are using at ECMWF, and what I will show is mainly work done together with Martin Leutbecher and Glenn Schatz, but of course there were many more people contributing to the development of the stochastic parametrizations. And as you would expect from the European Center for Medium Range Weather Forecasts, the main objective is to produce weather forecasts. So I will mainly talk about weather forecasts and not climate forecasts. But the good thing is that Tim pointed out earlier this week, we can verify the weather forecasts quite well, and so we can see the impact we get from our stochastic schemes and see what the quality is we get from them. Yeah, I will just give a short overview over the forecasting system at ECMWF and then introduce the two main schemes we are using, the stochastic caliper parametrization tendency scheme, short SPPT, and then the backscatter scheme Glenn already talked about a bit on Monday. And then I also remind you very quickly about what Glenn already said, and then I also show some other directions we were exploring. Well, the main things you need to produce a good weather forecast is a good numerical model. You also need good observations to get an accurate initial state, and then of course you need a big computer. And over the last few decades all of this was improved quite a lot and can be summarized in this picture where you have pairs of two curves. The thick curve is for the score for the northern hemisphere and the thin one for the southern hemisphere, and the different colors are different forecast lead times from 3 days to 10 days. And it's the anomaly correlation of the 500 hectopascal geopotential height. And you can see at the bottom you have the years from 81 to 2009. There's a steady improvement in skill in all curves, which is more pronounced at the southern hemisphere, which was able to catch up with the northern hemisphere due to the more and more use of satellite data, which improves the initial state on the southern hemisphere. And you can summarize this by looking at this. A day 7 forecast in 2009 was as good as a day 5 forecast 15 years earlier. So despite all these improvements, you might be surprised, but weather forecasts can go wrong. And there are three main reasons for that. One is the initial uncertainty, simply by poor coverage of observations or observation quality. Then we have uncertainties in the model, because the model is never a perfect model of the atmosphere. There are always uncertainties. And then the atmosphere itself is a bit chaotic at times, and that all adds up to uncertainty. And to address this uncertainty in the weather forecasts, the idea is to produce probability forecasts. So you don't only forecast one state, but you try to forecast the PDF of your forecast. So you start off with a PDF at initial time, and then you do many single forecasts to get a PDF of the forecast. And that gives you a measure of how reliable your forecast is. So if the spread is small, then you can be certain that the forecast is quite accurate. But if you have a strong spread, then you see that there's some uncertainty in the forecast. And you also get some idea about extreme events if you have peaks at the far end of the distribution. Well, part of what is on this slide I already said. You get an idea of the predictability of the atmospheric state at the moment. And if the system is well tuned, then a small spread means that you have a very accurate forecast. But if you have a big spread, you have a large uncertainty. And another point is that ensemble forecasts are more consistent than single forecasts. If you look at a single forecast, it can jump from one forecast to the other quite a lot if it's an uncertain situation where it is rain or not rain, but the ensemble forecast is in most cases more consistent in time. So you get 50% probability, but you get also 50% probability in the next forecast. And you can also measure the economic value, and I mean, the energy trading business is using ensemble forecasts quite a lot for their planning. Well, what is the ECMWF forecast system? It's mainly one software package which is called Integrated Forecasting System, and this is mainly written in Fortran and has also scripts for the initial starting and so on. And the main components of the IFS are the data assimilation system with a deterministic four-dimensional variational analysis. And since June, there's also an ensemble of data assimilations where you create an ensemble of data assimilations by perturbing the observations and by using model uncertainties as well in the assimilation process. And then the core thing is, of course, also the atmospheric model. I will tell you a bit more about that on the next slide. And then there's also a wave model and also an ocean model, also that's not strictly speaking a part of the IFS. Yeah, the atmospheric model is a spectral model with semi-Lagrangian advection. It's a semi-implicit time-stepping formulation. The grid point calculations are done on a reduced Gaussian grid, and in the vertical we use hybrid coordinates which are following the orography at the lower levels and then go to pressure levels higher above. Yeah, the prognostic variables are wind or vorticity and divergence in spectral space, temperature, humidity, and the logarithms of the surface pressure, but there are some more as well, which are not that well important. Yeah, and then there are, of course, a range of parametrizations for radiation, convection, diffusion, and so on. Yeah, what are the main products at ECMWF? That's the deterministic forecast, and it's a T1279L91 forecast, and these cryptic numbers simply mean that you resolve 1279 waves around the great circle on the globe, and the L91 stands for 91 levels in the vertical. And the corresponding grid length for the spectral resolution is around 16 kilometers. And there are done 10-day forecasts are started twice a day at 0 and 12 UTC. Then the other medium-range product is the ensemble prediction system, which consists of 51 forecasts, where one is the control forecast, and there are 50 perturbed forecasts. And they are done with variable resolution. So you have a 31 kilometer resolution in the first 10 days, and from day 10 to day 15, it's only 65 kilometer resolution. Yeah, and there are also 2 forecasts done each day as the deterministic at 0 and 12 UTC. And the initial uncertainties are represented by perturbations from the ensemble data assimilation and by singular vectors, which are optimized for a total energy growth over the first 48 hours of the forecast. And the model uncertainties are represented by the 2 schemes I will point out in detail in the following. And then there are further products. That's the monthly forecasting system. That simply once a week the ensemble forecast is extended up to 32 days, and with the only difference that it is a coupled run with ocean. And then there's the seasonal forecasting system, which has a 130 kilometer resolution. It's of course also coupled to an ocean model. The initial perturbations are again from singular vectors and from sea surface. And there are sea surface temperature perturbations. And there is once a month a 7-month forecast with 41 members, and once a quarter there is a 13-month forecast with 11 members. Yeah, giving a motivation for the use of stochastic parametrization is after this week maybe not really necessary, but the forecast error, as I pointed out before, has 2 parts, the initial error and the model error. And if you only have the initial error representation in the model, it turns out that you are under-dispersive. That means that the error of the forecast grows faster than the spread of the forecast. And then that means again that your forecast is overconfident because you have less spread than your forecast is uncertain. And sources of the model error are based in the model formulation in terms of parametrization choices, or simply if you use a grid point or a spectral model, then you have statistical fluctuations in the subgrid scale processes which you can't really represent with your bulk parametrization tendencies, and then there are unrepresented processes which aren't even in the model. And what we try with our stochastic parametrization is to represent the random part of all these errors. And in order to explain it to you, I have the one equation, which is an idealized model equation. So the local tendency of one of your prognostic variables can be written as a sum of the resolved scales, which we like to call dynamics. Then you have the parametrized quantities, which we tend to call physics. And then there is a horizontal diffusion term, and then you can add a stochastic perturbation term. And the first implementation was done in 1998, and the idea was to have perturbations which are proportional to your physics tendency. And so it was simply the perturbation is a random number multiplying this total parametrized tendency. And as you can see from the x and the random number, each of the perturbed parameters, so the wind components, temperature and humidity, each had an own random number. And the random numbers were uniform distributed between minus 0.5 and plus 0.5. And to have temporal and spatial correlations, the random numbers were constant in a 10 by 10 degree latitude-longitude box and kept constant for 6 consecutive time steps, which is, depending on resolution, 2 to 6 hours. As you will see a bit later, it's not really natural, and a pattern doesn't look really natural, and it also had some problems. For example, there were a too high frequency of strong precipitation events forecasted, so the idea was to revise this scheme, and that was done by using a different pattern. And that's a pattern which is very similar to also used in backscatter, so I will introduce how the pattern is done. So just a short note on how the triangular spherical harmonic expansion looks like, and it's your grid point value, so it's latitude, longitude, the vertical level, and time is given by spherical harmonic expansion, where you have your spectral coefficients and there's the spherical harmonics. And the new pattern evolves this spectral coefficients with a first order autoregressive process like this, where you have the at time t plus 1, your spectral coefficient is simply the memory term from the time before and the random term here. And this memory term governs the temporal correlations. So we have this decorrelation time in the exponent. So the longer the decorrelation time, the bigger the memory. So you get longer time correlations. And the random term has this sigma in it, which you can use to control the spatial scale of your pattern. And then there is this f naught, which is a scaling constant, which is used to give your pattern some other properties, which I will point out on the next slide. Well, and in spectral space, the variance is this, but just for information. So for the revised parametrization tendency perturbations, we use a constant temporal correlation, which is not wave number dependent. So it's 6 hours for all scales. And then you have the spatial correlation is given by a Gaussian in total wave number, which has this L parameter in it, which can be regarded as a decorrelation length on the sphere. And the scaling is done in order to get a certain variance in grid point space. So this complicated pattern simply changes the autoregressive process in a way that the grid point variance is fixed, which is used in the scheme. And now I have an animation of the two patterns. You see here the old pattern with the 10 by 10 degree boxes, which changes only every 6 hours, which doesn't look very natural, as I said. And then you have the new pattern, which looks much more as something you would expect to see on a weather map. So you have structures which are evolving slowly in space and time. Yeah, and the new scheme is very similar to the old scheme. You just use another pattern, and another big difference is we now use the same random numbers for all variables. So you don't perturb temperature and humidity in different directions, but you perturb them together, keeping more in the way the model wanted to go. Yeah, and this scheme is in the model now almost a year, and it uses a standard deviation of 0.5 in grid point space, and it is to avoid very large perturbation. The distribution is cut at 3 standard deviations. Yeah, the pattern which is used is the one I showed before, and there's also this additional factor which simply tapers the perturbations in the lowest levels and in the very high levels. And the code already allows to have multiple patterns for different temporal and spatial scales, and that's exactly what the next step is. The next step is to use a multi-scale pattern with 3 different scales in space and time. I give you the numbers on the next slide, and this is planned to be implemented soon in autumn. And it also contains some more specialized changes. It has a different treatment of supersaturations, because by perturbing your tendencies you can force the model into a range where the model is supersaturated, and you want to avoid this. And there was another problem with small numerical instabilities. If the random number was -1, then you switch the sign of the parameterized tendencies, and then that can lead to instabilities. So that's done as well. And that's now the 3 patterns which are used. There's the one pattern which is already used now with 500 kilometer decorrelation time and a 6-hour time scale. There's a second scale with 1,000 kilometer and 3-day decorrelation time, and then there's the large scale pattern with 2,000 kilometers and a 30-day scale. And what you see here is a time series at a single grid point, and you can see the variance of the small scale pattern is much bigger than for the slower time scales, and yeah, you can see how they change in time. And what we use as pattern now is simply the sum of these 3 patterns. Yeah, and the other scheme is the stochastic backscatter scheme Glenn already introduced, and the idea there is that a part of the kinetic energy which is dissipated in the model would actually be transferred upscale and act there as a stream function forcing on the resolved scales. And that also includes an interaction of deep convective organized convection on the resolved scale flow. And the stream function forcing is again done with a pattern generator, and the pattern is modulated by a total dissipation rate to get it more flow dependent. So you want to put in the kinetic energy where the model was dissipating it, and not everywhere. And it also contains this backscatter ratio, which is our main tuning parameter, where we can tune how much energy we put in. Yeah, the pattern generator is, as I said, very similar to the one used in the other scheme. We also use a constant decorrelation time at the moment at 7 hours, but the spatial correlation is done in a different way. We use a power law for the wave number dependency. And in the SPPT scheme, the same pattern is used in the whole column. But for a backscatter, we also have vertical correlations, and they are simply introduced by having a random phase shift of the random numbers used in evolving the pattern with height, and that gives a certain profile of correlations. And you see you have this random number in the phase, and you have this vertical structure because the phase shifts are different in the boundary layer than they are higher above. And the scaling is now not done to get a variance in grid point space, but now the scaling is done to normalize the energy input of the pattern, because we want to modulate the energy input by dissipation rate. So we normalize the energy input of the pattern. Yeah, how is this dissipation rate done? It can be confusing. We call it the total dissipation rate, but it actually isn't the total dissipation rate the atmosphere would see. What we consider in the dissipation rate is a numerical dissipation, which should be the kinetic energy lost by horizontal diffusion and by the diffusion which is implied by the interpolation in the semi-Lagrangian advection scheme. Then we use the dissipation from the gravity wave parametrization. Then, as I said, we have this deep convective kinetic energy production, which is estimated from the mass detrainment rate and the mean vertical velocity, which we get from the convective parametrization scheme. What we don't have in our total dissipation rate is the boundary layer dissipation, simply because we assume that this boundary layer eddies are so small that they don't project on the quasi-balanced large-scale flows. And if you then look at the stream function forcing we're putting in, the left picture is the stream function forcing and the right picture is the corresponding vorticity forcing. And well, you can see the pattern is similar to the one of SPPT, but since we are forcing vorticity in the model, it's much, it's more small scale as you would expect if you look at the stream function forcing. So, and where are the schemes now used? And it's in black there are the schemes used at the moment, and in gray are the changes which should be implemented shortly. At the moment, the EPS system uses this one scale SPPT pattern, but that, if everything goes well, this will be updated to a combination of the 3-scale pattern and backscatter with the next model upgrade. And to keep the ensemble data assimilation consistent with the forecast, it is planned to do this change there as well, but that takes a bit longer and is planned for next year. And also the seasonal forecasting system, which uses at the moment the old tendency perturbation scheme, because it isn't updated as frequently as the deterministic forecast, as the short range forecasts, is planned to update as well to the same setting with the next update in winter. Now that I told you all the background, I will show you some results to show you that it makes sense to do all the stochastic forcing. This is a plot of 850 hectopascal temperature in the northern extratropics. The scores are derived from 40 ensemble forecasts we did for 40 start dates. And you see there are the curves with symbols, which are the root mean square error of the ensemble mean. And the lines without symbols is the ensemble spread. And there are 3 experiments. The blue one is for no stochastic perturbations. Then there is the black curve, which only has the 3-scale version in it. And then there's the red forecast with the combined schemes. And you can see not only spread, the spread goes up quite a bit by adding the stochastic schemes, but also the RMS error goes down. So you see that you don't simply add noise, but you add noise which makes sense. And you also see that if you look at probabilistic scores, I have again this continuous ranked probability skill score. So a perfect forecast would have a score of 1, and the forecast with a score of 0 means that you don't have any impact, you don't have better results than a climatology forecast. And you can see also in this score you are improving by adding the stochastic schemes. So that's again for the northern extratropics. If we look at the tropics, the impact is much more pronounced. So you can.
Could I just, in case people kind of could conceivably get misled by this, when you say the northern extratropics, you don't mean the whole average temperature for the northern extratropics. You're taking the scores at all the individual grid points.
Yes.
And averaging that over the northern extratropics.
Yes.
Because otherwise it might seem a bit bizarre that scores would go to 0 for such a large scale average field. That's not what you're showing.
Yeah.
Just to be clear, it's like a question some people might be confused about.
Yeah, now the scores for the tropics, which show a much better impact, so you can get more excited about them. You see a really big improvement in spread, and you see also a very big improvement in the root mean square error. And also the probabilistic scores go up quite a bit. So there's really a good impact in the tropics. And to show you some resolution dependency, and to show you how magically the stochastic schemes can look, I have some older results. There are now a lot of curves in it, and you can't distinguish the colors very good. But what it should tell you is there are unperturbed runs for 2 resolutions, so 130 kilometers and 50 kilometers, which are in green. And then you have, for the same resolutions, a forecast with the perturbed tendency scheme, and then you have again a forecast with the combined schemes. And the 2 unperturbed that's again this skill score, and the unperturbed forecasts are here and here. So you see, by adding the stochastic schemes, you can outperform even a forecast at twice the resolution. And you could even say that this light blue curve is as good as a high resolution, which is backscatter, and the perturbed tendency is as good as a forecast with a much higher resolution with the perturbed tendency scheme alone. So as I said, that looks almost like doing magic, and you have this result in the tropics, but of course if you go to the extratropics where the model is much better anyway, you don't see that you can't outperform a higher resolution. You still have a good impact of the stochastic schemes, but you can't get up to the amount. So the thin line here would be the high resolution without perturbations, and the thick line is the one with both schemes in it. So you come close, but you can't replace a resolution increase with simply adding some stochastic parametrization. And then the other point Glenn already made on Monday is that besides the good improvements you get from stochastic parametrization, improving the model is always another thing you should keep in mind. So that's, again, the blue line is the old model version without any perturbations. The red line is the old model version with the stochastic schemes in it, so you see a big improvement in RMS error and spread. But then you have this dotted line, which is the new version with the stochastic schemes in it, and you see that it improves again quite a lot just by improving the model. Yeah, and to show also results from the seasonal forecasts, I have results for the sea surface temperature in the Ninyu 3 region, which you can see in this top right picture. And you have again the RMS error, which are the continuous lines, and then you have the ensemble spread, which are the dotted lines. And there are again 3 experiments. You have the control run, and the control in this case is not without any stochastic forcing, but it's with the old stochastic scheme, and this is operational in the seasonal forecasting. And then there are 2 implementation of the 3-scale version, where the difference is that the standard deviation of the 30-day scale is larger in the red forecast. You can see you get again an improvement in spread by using this new stochastic scheme. And by playing with the standard deviation, you can even get very high spread, which the seasonal people didn't like. So the blue line is what is going to be in the model. And another thing which you can see from long-range forecasts is that you also have an impact on systematic error in the model. What you see here is precipitation. These are difference maps. So the top is the difference between the control run and the observations. You see the model has, without the stochastic schemes, a large bias in the tropics. And if you then look, I mean, it's not that the stochastic physics improve it to look like this. It would be very nice, but that's the difference between the forecast with stochastic forcing and the control run. You see, so in this region, the run with the stochastic forcing has less precipitation, and if you look here, that's exactly a region where there's too much precipitation in the control run. And also these other regions are quite well, have all the opposite sign of the error in the forecast. So there is a impact on systematic error as well. Well, that's again what Glenn already said. All these parameters we are using we try to get from coarse graining to have a justification for using them and not simply tune them to the best values. And what was done was to look at cloud resolving model data, and then there were also the experiments Glenn described where high resolution forecast data was used and taken as truth, and then the difference to the low resolution forecast were taken. And for the SPBS scheme, we used it to define the spectral power distribution and also for defining the vertical correlations. And I think Glenn already had this picture, so you can see there's the stream function forcing spectrum from the IFS coarse graining, which is the black line. Then you have the forcing from the cloud resolving model coarse graining, and the red line is what we are putting in the model. So you see we are nicely between the results of the coarse graining. Yeah, I showed you now what we've done so far, and now a bit of an outlook what still can be done. As I said, the SPPT scheme is perturbing the total parametrized tendency sum. So you add together the tendencies from convection and from the cloud scheme and so on. And maybe it would be better to address all these different perturbations on their own to account for the uncertainty in each scheme. And for backscatter, there is also quite some potential. So far, we only backscatter kinetic energy, but you can also think of backscattering temperature to have kind of an available potential energy backscatter. And then, as I said, we're using constant decorrelation times in backscatter, but the decorrelation time will also be scale dependent, so that's another thing we could try. And then there's always this thing that we have this pattern, but the pattern sticks more or less locally, but you can imagine that the small scales are affected quite fast, so it might be helpful to affect the spectral pattern as well. And then there are totally different directions which we are thinking to go at. And one is, Tim showed that in 2 meter temperature the results weren't that great with the stochastic physics compared to the multi-model at the moment. So one idea is to have additional perturbations of surface fluxes and of radiation, and together with that maybe clouds, which of course act on the radiation. And another thing is representation of convective cell organization with a cellular automaton, which is coupled to the convection scheme. And I did some work on that, and I will show you in the following. Well, I don't know if you're all familiar with the cellular automaton, but the idea is to have some discrete rules which determine the next step in the CA. And I have an example for the rules which are here. So if you have 2 or 3 neighbors, then a new cell is born, and a cell survives if there are 3, 4, or 5 neighbors. And if you start off from this block of 4 cells, then you get an evolution which looks like that. And actually in the first implementation of the backscatter scheme, there was a pattern used which was based on a CA. And inspired by forest fire simulations which use probabilistic CAs, I also changed to a probabilistic CA, and now the birth and survival of cells is not given by a deterministic rule, but it's now given by probabilities. So I plotted the probabilities here, so you see the deterministic case, which is a special case of the probabilistic case would have probability 1 for these 2 and 3 members, but if you use a probabilistic, you can have this probabilities like that. And that allows for easy coupling with model fields, because you can simply based on a model field, for example, CAPE or moisture convergence, you can change the probabilities and so get more an interaction between model and the pattern. And just to show you how this impacts on the CA, in the top is the deterministic one, and at the bottom is the probabilistic one, and again starting from a single cluster of points, and you see that the probabilistic has more this nice circular shape, which I like more than this squared shape. So another improvement, if you like, so was that I implemented the CA on the model grid. So it's not longer on a special grid as before, which was a latitude-longitude grid, but now it uses the model's Gaussian grid, which is first better to get it coupled with model fields, and then you save quite a lot of computational time because you have this reduced grid. And the other thing is you can use the parallelization in the model, so it's highly parallelized then. And there are two options to have a global pattern, or one which is coupled to the convection. And you have this two-way interaction then between the model and the CA. So the model acts on the CA by, for example, attracting the pattern with the model winds. Or, as I said before, you can make the number of lives a function of CAPE, for example. And you can also make places where you seed new cells depending on some model field, for example, points with deep convection. And the other way around, you can force the model with the CA. And things I tried was to modify the temperature and humidity profiles which are going into the convective parametrization, or to modify adjustment time or entrainment rate, or to simply modulate the convective tendencies with the CA. And there are some nice patterns just to show you how they look like. The top one is the global pattern, and the bottom one is the one which is coupled to the convection scheme. So you see that one is restricted to the tropics, while you have here this global pattern. You can also see nicely this attraction in the storm tracks and in the opposite direction in the tropics. Yeah, unfortunately the results are not as nice as I would wish so far, but I can show that there's an impact by doing this, and there are also some good results. That's again the precipitation, and that's from 18 long-range forecasts which were started each on the 1st of November and carried out for 1 year. And I show the mean precipitation for April to June. And in this run, the output from the convective parametrization scheme was perturbed. You see again the difference between control forecast and observations, and as before you see this big bias in the tropics, and then there's the difference between the perturbed CA run and the control, and you can again find regions where it's improved. Here in front of South America is an improvement, also here, but then you also see regions where it's getting worse, like here there's more in the CA run and there's already too much here, so it's not totally right. Yeah, just to summarize where we are now, so I've showed you there's a noticeable impact in probabilistic scores and in spreads, so you can see that the stochastic schemes are doing a good job. Then one advantage we have over the multiphysics approach is that we only have to maintain one model. And I think the Canadians, which used to do a multi-model ensemble, went also to stochastic parametrization simply to keep the maintenance work down. And then I also made the point that you also see an impact on systematic errors and not only on the spread. And then there's just a small wish list. So you would think that it would be a good idea to also put model error representation in the ocean models, and maybe it would also be better to represent these stochastic processes directly in the parameterization schemes instead of bolting it on top like we do it at the moment. And just some commercial for a paper we did last year, which you can download from the web page, where you can find all this background I told you about. Except the latest results are of course newer than 1 year. Thank you.